So, hello everyone, we are going to start the second lecture of week 4, that is applied enzyme catalysis. So, in this lecture we will be discussing particularly external mass transfer, and in the next chapter we will be discussing internal mass transfer. So, if you remember the last lecture, we discussed what is immobilization, confining the enzyme into space, particularly into some solid matrix, and why we are doing it, so that we can reuse it, we can improve its stability, which are essential for actual industrial applications. Then we discuss different enzyme immobilization techniques. For the soluble enzyme, we mostly go with this ultrafiltration. For the insoluble enzyme, we either go for carrier binding. Now, the carrier binding, we can have 4 different type interactions for carrier binding: physical adsorption, covalent linkage, ionic interaction or metallic interaction. In addition, there is one method of cross linking. So, in the cross linking, we use cross linker molecule which attaches to enzyme molecules. In addition to the cross linking, we also discuss entrapment. So, we can entrap one enzyme in the fiber or in the microencapsulation methods. Then we discuss what are the advantages, particularly merits and demerits of enzyme immobilization. Now, what we discussed in the last class, this when you are immobilizing the enzyme, it can impact the kinetic parameter both Km and Vmax. In addition, it can also impact the concentration of the substrate. So, when it is going to impact the concentration of the substrate, that comes under the purview of external and internal mass transfer. So, today we will discuss how to define the effectiveness factor, means what is the rate of reaction in the absence of immobilization and in the presence of immobilization, and today we will discuss about external mass transfer. So, effectiveness factor, as the name suggests, how effective is the immobilization. So, it says you have that reaction rate in the presence of immobilized enzyme and rate when no mass transfer resistance, it means free enzyme. So, the ratio, typically the observed rate will be lower than that of the rate with no mass transfer resistance. So, it says the maximum value of eta can be 1 when there will be no mass transfer resistance, and whenever there will be mass transfer resistance, eta value will be less than 1. So, for example, if you see here Michaelis-Menten parameter for a soluble enzyme for a certain substrate are found to be Km 0.05 millimole per liter, R max 10 mole per liter. Now, after immobilizing this enzyme on the surface of an insoluble matrix by physical adsorption, which method is being applied? Physical adsorption. It was found that Km apparent value increased. So, Km has increased to 0.08. It means the substrate specificity has decreased. The apparent maximum rate remained the same as R max. So, R max was 10 mole per liter, or you can say the V max was the 10, V max there is no change, there is no change in the V max. It says what is the effectiveness factor of the immobilized enzyme when substrate concentration is 1 mole per liter. So, what we have to do here? We have to calculate rate V max CS upon Km plus Cs. So, in the case of free enzyme, what was the value of V max? 10 mole per liter per minute, concentration Cs is 1. What was the value of Km? 0.05 plus Cs 1. So, we will get rate as 9.524 mole per liter. Now, in the case of immobilized enzyme, V immobilized enzyme, this will be formula will remain same, V max Cs divided by Km plus Cs. Here the Km value have increased to 0.08. So, this will be 10 into 1 divided by 0.08 plus 1 is equal to 9.25. So, you can see the rate has decreased. Now, what will be the effectiveness factor? It says rate for immobilized enzyme divided by rate of free enzyme. So, this is 9.259 divided by 9.524. It means effectiveness factor is 97%. Now, here we did not consider the mass transfer resistance. What will happen in case of mass transfer resistance? Apart from change in this kinetic parameter Kn and Vm, this Cs will also be changed. So, now we will be referring to Cs. One we will be referring Csb, what is the concentration in the bulk, and when it is coming to the enzyme surface, this concentration will be referring Cs. Now, Csb will be higher than, typically this Csb will be higher or equals to the Cs. Now, once you have immobilized the enzyme, you can see there are three observations. What are the phenomena happening? Then how the concentration profiles changes, and what are the parameters one need to see. So, in case of immobilized enzyme, we just see substrate has to transport through external film. So, that is when it is transporting through the external film, there is a mass transfer here. Then after reaching to the surface, it permeates to the enzyme surface, there is a formation of product, then product is coming at the surface, then again it crosses the film and it transports bulk to the solution. So, there is a transport of substrate and inside and transport of product outside. The top section present the key phenomena such as substrate diffusion, enzymatic reaction, product formation. So, these phenomena lead to the substrate and product concentration profile. If you just see the substrate concentration profile, because enzyme is exposed to substrate from both the sides. So, this will be the maximum substrate concentration, it keep on decreasing, typically at the center it reaches to its minimum value. Similarly, what happen as the product is being formed at the center, product concentration will be higher here, it will keep on decreasing and it will reach to the plateau when it is going outside of the bulk. So, you can see the different profile of the substrate and product due to enzyme immobilization. Then the bottom section says quantitative parameter I diffusivity, V max, Ks mass transfer coefficient necessary to describe and model this concentration profile. Means theoretically we should be able to predict this concentration profile using the concept of mass transfer. The mass transfer coefficient Ks and diffusivity coefficient Des. So, the same is summarized here. What are different influencing factor? There is support material, it can affect both external and internal mass transfer. Now, what is external and internal mass transfer? If I go back to the last slide, travelling from the bulk to the bulk to the surface, this is called external mass transfer. And when it is travelling from here to the enzyme surface, means inside the solid matrix, that is called internal mass transfer. So, the support material is going to affect both external and internal mass transfer. This porous nature is again going to affect both external and internal mass transfer. Further, hydrodynamic condition, what is the agitation, what is the flow rate, whether this is aerated, whether it is stirred or not. So, depending on that, that is going to affect the only the external mass transfer or the film mass transfer resistance. Then enzyme distribution inside the solid matrix, it is not going to affect the external mass transfer, rather it is going to affect the internal mass transfer. If it is immobilized on the surface, it is going to decrease the internal mass transfer resistance, and if it is within the pore, it will increase the internal mass transfer resistance. So, now let us see this how this mass transfer is taking place. As I told, we are considering the concentration of substrate in the bulk CSB, and which is reaching at the enzyme site, the concentration is CS. Now, it is there in the bulk, from the bulk it has to cross the film and then it has reached to the surface. So, this is the first resistance, and then once it has reached to the surface, now it has reached to the active site of enzyme. So, this is the second resistance, it is facing two resistance. The first is transfer from the bulk liquid to the liquid layer surrounding the immobilized enzyme. Second, diffusion through the relatively unmixed liquid layer or film. Third is diffusion from the surface of the particle to the active site of the enzyme in an inert support. Now, from these three steps, when we are discussing 1 and 2, that is called external mass transfer resistance, and step 3 is intraparticle mass transfer or internal mass transfer. So, today's lecture we are going to discuss this external mass transfer resistance. So, as we have seen, in the case of external mass transfer, we are considering this is solid matrix, there is a film and through which your substrate is crossing, right, CSB. So, as this is a film, so we typically apply the film theory and simple this nearest diffusion layer or stagnant film model describes the mass transfer here. So, it says the rate of mass transfer will be Ns equals to mass transfer coefficient Ks A interfacial area to CSB minus Cs. So, CSB minus Cs, this is the driving force, concentration difference. Ks is mass transfer coefficient, A is interfacial area, it says total surface area per unit volume. Now, during this enzymatic reaction, let us say if it is steady state, then whatever substrate is coming at the enzyme surface, same is being utilized through enzymatic reaction. So, it says the both the rate of substrate in and rate of substrate consumption should be equal. The rate of substrate transfer we have already discussed, K as A CSB minus Cs, this should be equals to the substrate consumption rate. So, let us assume it is following Michaelis Menten equation, the substrate consumption rate will be V max C s upon K m plus C s. Why we are writing C s here? Because C s is the reaching at the enzyme surface for the reaction. C s b is not directly coming for the enzymatic reaction. Now, we had the equation K s A C s b minus C s equals V max C s upon K m plus C s. This equation can be simplified in dimensionless form. So, for this we are going to use certain parameter, we say x as C s upon C s b, and the term you are going to use kappa as K m upon C s b, and one more term you are going to use dA, that is Demko-Heller number. dA is Demko-Heller number, which says maximum reaction rate V max divided by maximum mass transfer rate. Maximum mass transfer rate will be, what will be the maximum mass transfer rate? It says K s A C s b minus C s. So, when C s is 0, that time it will be maximum mass transfer rate. So, it says K s A to C s b. This is Demko-Heller number. So, based on Demko-Heller number, one can decide whether mass transfer resistance is present or not. So, if you can simplify this expression, then this will be C s will be in terms of x and K s will be in terms of K s a will be in terms of Demko-Heller number. So, K s a will be dA, you can rearrange here, K s a is V max divided by dA C s b. So, it says V max dA C s b, and let C s b be common from here. This will be 1 minus C s upon C s b. C s b is cancelled out here. Now, V max will be again cancelled out from here to here. We are left with C s upon K m plus C s. So, it becomes 1 minus x divided by dA, this equals C s upon C s b x K m upon C s b kappa plus C s upon C s b x. So, we end up with 1 minus x upon dA equals x upon kappa plus x. Now, considering this, we will be briefly discussing the significance of Demko-Heller number. So, it says Demko-Heller number is the ratio of maximum reaction rate V max upon mass transfer rate. Now, there can be two cases, if Demko-Heller number is less than 1 or Demko-Heller number is greater than 1. If Demko-Heller number is greater than 1, it means K s a value is low. When K s a value is low, what does it mean? Mass transfer coefficient is low. It means there is a large mass transfer resistance. Here what it says, Demko-Heller number is higher, Demko-Heller number is less than 1. It means mass transfer coefficient value is very high, and when K s value is high, it means there is a low mass transfer resistance. So, when there is low mass transfer resistance, we say this is a reaction limited region, means V max is dominating here, this is dominated by the V max, and when it is a diffusion limited region, it means this is dominated by K s. So, if Demko-Heller number is greater than 1, this is a large mass transfer resistance or diffusion limited region, and Demko-Heller number is less than 1, low mass transfer resistance, Ks value is high, and this is a reaction limited region. Now, we can go back again to the same expression. It says 1 minus x upon dA equals x upon kappa plus x. So, we can try to solve this expression. So, if you just rearrange this will be kappa plus x minus kappa x minus x square dA dx, and if I am going to rearrange this, then this will be x square plus x, this will be dA plus kappa minus 1 plus 1 equals minus, it is going to other side. So, this will be minus kappa 0. So, you can see this is a simple quadratic equation. It says ax square plus bx plus c equals 0. This is a quadratic equation, and here the solution for this quadratic equation is x as minus b plus minus under root b square minus 4 ac upon 2a. Now, to solve this in this form, what we can do, this the coefficient of x is k plus dA plus 1, that we can simplify as beta. We are going to use another term, that is called beta, beta as kappa plus dA plus 1. So, the coefficient b is beta here, this term we are referring as beta, a is 1 and c is minus kappa. So, it says x equals minus beta plus minus underscore beta square minus 4 ac, 4 a value is 1, c is kappa. So, it becomes plus 4 kappa whole upon 2. So, what we can rearrange, we can take this beta upon 2 common from all. So, this will be beta upon 2. Let us take here, this is beta square. So, this will be under root beta square will be 1 plus 4 k upon beta square, and if you divide this by beta, it will be minus 1. That is it. So, it is simply rearrange it. So, it says x is beta upon 2 1 minus 4 k upon beta square minus 1. This simple quadratic equation, it says it is possible to get the value of Cs. X is, what is x is Cs upon Csb. So, analytically this can be solved to get the value of concentration at the enzyme surface, which will participate in the enzymatic reaction. Now, let us, if you put here in this expression beta as 0, if I put beta as 0 here, so this x will be only this term 4 k. So, this will be under root 4 k, means 2 will come out, 2 under root k upon 2, it will be only under root k. So, x will be under root kappa, and what is kappa? Km upon Csp. Now, once we have discussed what is changing here in the case of external mass transfer, Csb is decreasing to Cs. Now, we can calculate the effectiveness factor. Let us say calculate effectiveness factor considering the Michaelis-Menten equation. A reaction observed rate, what will be the concentration in this case? Cs. So, this will be V max Cs upon Km plus Cs. Reaction rate with no mass transfer resistance, then what will be the Cs? It will be Csb. it becomes V max CSB Km plus CSB. Now, if you remember what is the x? X is Cs upon CSB and kappa is Km upon CSB. So, you divide by V max is the cancelled out here, you divide by the CSB. So, this becomes x upon kappa plus x equals CSP upon CSP 1 divided by kappa plus 1. So, in this way we can calculate the effectiveness factor, and if effectiveness factor is 1, then CS will be equals to CSB. So, the rate will be V max CSB upon Km plus CSB. We will have a quick example here only based on external mass transfer. It says denitrifying bacteria are immobilized in gel beads and used in a stir tank reactor for the removal of nitrate from the groundwater. At a nitrate concentration of 3 gram per meter cube, it says CSB is 3 gram per meter cube. Conversion rate V is 0.011 gram per meter cube into second. Effective diffusivity for the nitrate gel is 1.5 into 10 to the power minus 9 meter square per second. So, this effective diffusivity is different from the diffusivity. This we will be discussing in the next lecture when we will discuss internal mass transfer. Size of the bead is 6 mm in diameter. So, D is 6 into 10 to the power minus 3 meter, or R will be 3 into 10 to the power minus 3 meter. Km for the immobilized enzyme is 25 gram per meter cube. Now, today we are only going to discuss external mass transfer resistance here. The same example we will be discussing at the end of internal mass transfer as well. Then we will see whether both the mass transfer resistance are present or not. So, for the external mass transfer, what we need to do today, considering the external mass transfer resistance, estimate the concentration in the bead. So, CSB is here, what you have to do? We have to find the value of CS. So, we can simply apply the equation, that is a rate. What is the rate? V equals Ks mass transfer coefficient. Yeah, the liquid solid mass transfer coefficient is 10 to the power minus 5 meter per second. Ks is 10 to the power minus 5 meter per second. Ks A CSB minus CS. What is the A? Is the interfacial area, means surface area per unit volume. If you consider the sphere, area of sphere will be 4 pi r cube and volume will be 4 pi r square and volume will be 4 by 3 pi r cube. So, pi is cancelled out. This will be interfacial area is 3 upon r. Now, you can put Ks into 3 upon r. CSB is 3 gram minus CS we have to find out. So, all other parameters are there. What is the value of Ks? Is 10 to the power minus 5, R is 3 into 10 to the power minus 3, V is 0.11 gram per meter cube into second. So, if you put this value, you will get the value of CS as 1.9 gram per meter cube. So, you can see there is a significant decrease in the concentration. So, you say CS is much lower than CSB. It says this is the effect of external mass transfer resistance. So, we will stop here. So, today we discussed in case of immobilized enzyme, apart from there is change in the kinetic parameter V max and K max, Km, there is a change in the concentration profile as well, and substrate concentration profile decreases from the bulk to the center of the immobilized enzyme, and vice versa profile is followed for the product, and decrease in the substrate concentration from bulk up to the surface of enzyme, we consider it is having a film theory, and that is called external mass transfer resistance. So, today we discuss external mass transfer resistance. Further, the transport of substrate from the surface to the active site of enzyme will be considered in the internal mass transfer or intraparticle diffusion, that we will be discussing in the next lecture. Thank you.